All right, hello everyone. I'll try and make a start, given it's past 5:30 now. So my name is Stuart. I tutored this subject. I've done it 3 times now, but I was too busy this year to be able to squeeze it in, unfortunately. But I'm good friends with Bryn, who was organising this. Bryn asked me if I could help out. I was like, yeah, sure, because I helped edit these slides last year. I'm here with also with Paul. Are you?
Yeah, I'm doing it.
Yeah. Colton is a tutor extraordinaire. Been doing tutoring for a long time. Good person to have as a tutor. And yes, she's long gone, but shout out to Hi to Ahmed for putting these slides together. I was there when she presented the first version of this.
Back in the day.
Not when I was doing the subject, but when I started masters, I think. It's a whole story. So I'll start with acknowledgement of country or traditional owners. I'm sure you all know the Wurundjeri people of the Kulin Nation, the Aboriginal people of Australia who live in this area. Anyone can give an acknowledgement of country. It happens all the time. But what I find more interesting is like actually linking it to something. So I don't know if you can see a picture on the left, on the right, the giant face of the building. Does anyone know that building? If you're on Swanston Street coming up to Melbourne Uni before the turn, it's like at that point. So if you're on Swanston Street, you can see this building. And that thing on the left, that's the balconies of the building. So they've like cut it such that you see this guy's face. And that guy is William Gareth, who is a Wurundjeri elder. And I think he's pretty good there. It's quite interesting to read about some of the stuff that he did. He walked all the way from like I think rural Victoria to the steps of Parliament to like make a case for Aboriginal rights. And it's kind of funny because that same thing happened this week. I think there was a convoy of people who walked all the way to Parliament House in Canberra for Aboriginal rights for instance. So anyway, more you know, an actual local Aboriginal elder associate. More you know. Now, disclaimer, this is not officially endorsed, but we've worked on and around this content a lot and know the subject fairly well, so happy to present it. Here's if you haven't heard of CISSA, there's a QR code, you can find out more. And if you haven't heard about MISC, there's a QR code and you can find out more. So, where I start with this, we hope to like poll people to get a better sense of what areas of the subject you'd like covered the most. So this is my attempt to summarize the whole subject in dot points by area.
Maybe just poll you want it.
Yeah. Colin's got a separate approach for the networking side. But if we look at the left side of the screen, it's crypto and networking. But if we look at the left side of the screen from all those bullet points, I'll just talk through them and like stick your hand up if it's a topic that you'd like covered, or half if you interested, and I'll engage that based off the various reports. So general purpose of an operating system, this mechanics of a CPU, so things like interrupts, syscalls, user mode, kernel mode, processors, threads, the difference between processors and threads, synchronization of mutexes, virtual memory. Okay, so we've got synchronization. Sorry? Yeah. Sorry, again, virtual memory. Did I see a hand or two, or one hand? Oh, synchronization. Yeah, okay. So synchronization and scheduling. What was the first assignment this year? Was it another scheduling thing? Yeah. All right. You should be experts. Yeah. So there's a lot of content on all of these slides. The slides will be made available. Standing up here, Colton, I was saying, standing up here and just talking. The CPU. all have their own program counter or spot in program execution where they're at. Interrupts can go to one or more CPUs. That's a topic I'm not going to get into because it's well outside the scope of the course. But in general, what you need synchronization for is the fact that these monkeys are going like next instruction, next instruction, next instruction all the time. And whilst their own registers are separate, if they're operating in the same memory, you've got to make sure that they don't end up writing on top of each other. Because if they both write the same area of memory at once with two different numbers, only one of them will win, and the one that lost won't know that it even lost. And then you end up with corrupt data and stuff like that. It can be really bad if you're writing whole data structures and only half of one wins and the other half of the other one wins. And then you just end up with complete corruption and really annoying multi-threaded flows. So that's always been my analogy for a lot of this. I hope that helps set the scene, so to speak. Yes.
So those bugs can't happen if there's only one monkey.
That's a very good question. So parallel write bugs can't necessarily happen if there's just the one monkey, but this is another complicated topic in threading is that hopefully you're all aware, I'm pretty sure it's outlined in the subject, the difference between parallelism and concurrency, which is the difference between, there's many good analogies of it online. I think I was reading one the other day, but I can't remember what it is, sorry, but it's the difference between having multiple tasks on one CPU and swapping between one task at a time versus actually, like, when that happens, you're able to process work out of order and pause some work on other work, and then work on other work. And so at the top long view, it seems like multiple things happen at once, but in reality, only one thing is ever happening at once. Whereas concurrency is when you get to the point that truly, parallelism is the point where you get to truly multiple things are happening at exactly the same time. And that's the two monkeys scenario where the code is literally executing at the same time on two separate CPU cores. Two separate sets of code. So yeah, we've kind of got to flick through all this. What makes this complicated is as well the difference between a process and a thread. No, this wasn't what the section cover, but like in general, the key difference between a process and a thread is that threads share the same address space. They still have different registers, or like sets of registers that they use, or register values, and have a separate stack. But the stack's just at a different spot in the same area of memory. And the heap, so to speak, is the broader area of memory that they can both access all of the time. So what that means is that stack variables, which are local variables can see, are unique per thread because they're local to the thread because they're stack storage things. But whenever you call malloc, you get a pointer back that's somewhere on the heap. And then now all of a sudden, one thread might have a local pointer that points to position 27 on the heap, and the other one does as well. And all of a sudden, now you've introduced a shared resource that the two of them can contend over, and that's when you get into all the really problems. So we'll go through skim through all of this. Mode switch, system calls, interrupts. Oh, and again, it's also made confusing by the fact that, like, you can run multiple processes on a computer and technically have that can be called multi-processing. But then even so, within a process, you can have threads. So you can multi-thread within a process, but that can also happen only on a computer that has one CPU core. So you still have no true parallelism. You only have concurrency aspect of it. Whereas if you didn't have any threads and you just had processes, you can still get parallelism from different processors on different cores. But then you can't exploit that parallelism within one process and thus the one memory space. Because two processors can be the same program, but have a totally separate memory space that they're operating on. So the distinctions are fine and annoying, but make sense when you step through them and explain stuff. Sorry, this is further than I thought that we were going to have to get through. So this one's really. Is there actually a sec? Don't tell me there's not actually a section on synchronization. I swear there was a section on synchronization, unless it came under threads.
So it's just like
Implementation, the context switch. Maybe there wasn't actually a section on. That's embarrassing. Yeah. So, I mean, there's memory management. Yeah. Sure. Apologies. Hopefully, at least, I feel like synchronization in general, there's two types to think about. There's the true parallel thread synchronization, and that's where it makes the most sense because, like, any thread can be running any part of its code at any point in time. This is because, like, there's all sorts of non-determinism in a running operating system that comes from user input and hardware delay and network data being different and stuff like that. Whilst the operating system is a deterministic piece of code, you don't know how long it's going to take for a network response to come back. You have no idea when the user is going to move their mouse. So there's always a bit of noise coming into the system. That means that even though the scheduling algorithm is deterministic, you have literally no guarantee at all over the order in which things happen. There might even be a halting problem argument that you never have any idea what any one program is going to do at any point in time. But I won't get into that. Field computer science person. But because of that, again, you essentially have to make the assumption that literally any line of code that's being executed by different threads could happen at exactly the same time as any other line of code being executed. And in a true material sense, it's probably the CPU instructions, but that's close enough to line of code in C for it to make sense. And so that motivates why we need the synchronization of like a lock, because the lock provides a mechanism to get a yes or no guarantee that you've got exclusive access to something. And a lot of the time, the locking is performed by various CPU primitives. I think it's like test and set. Yeah, and stuff like that, where it's like, in the way that the CPU works, even though it's a CPU with, say, 4 cores, there are certain instructions that if you cause a test and set to occur, within all of the machinery of the entire CPU, there is a guarantee that if things happen, if all 4 cores happen, because I'm sure if you've played with threaded programming enough, you know that you can still have mutexes and threading bugs. If you don't lock the right things in the right order, you can have deadlock.
Yeah, it never works by trying to fix the problem
Yeah. Threading is in general very annoying. I'm sure you're all familiar with that. So I feel like, are there any more questions about synchronization, Jen? Are there any bits of it in the subject mentioned that are
clarified on the parallel kind of seeing it? Like, it's a different basically with the fact that multiple things that involve parallelism, but only one person sees it involved.
The parallelism, it means that it is actually possible for multiple things to happen simultaneously. Whereas concurrency purely just means that you can still work hard to the other person. So that's the best way to kind of. So you can still use threading to good effect on a single core computer. And part of the reason is that it just gives you the ability to pause work.
It's really important if you have tasks that don't really finish. If you've got a program on your computer, it doesn't really kind of finish. Like if you're running Microsoft Word or your browser, it doesn't stop. I think you have to kind of figure out when am I going to go run something else to work.
Yeah. So, yeah, it's the Mammoth My Turn on the Xbox thing. There's only one CPU. All the processes share that CPU. Just being able to pause individual things, or even within one process, like if you've got Microsoft Word, what's it? We've all dealt with programs where you click to do something and then it locks the whole UI thread and you can't use the entire app because it's just locked doing something else. That's an example of like bad threading programming, and that can occur even in a signal call context where it's like, say you're just waiting for a network request to come back. If you just block waiting for that, then you're blocked from being able to handle any other UI event, update the UI, respond to user things. In fact, usually when you get the spinning pause thing, what is happening is that the main UI thread of the application has become blocked. And Windows itself, or whatever, the OS, have mechanisms to detect that the main thread of an application is not checking in regularly enough. So that indicates that it's blocked. And that's why the window fades out, or like fades to gray. So it's going, maybe I remember, but does that answer the question? Yeah. So it's like, even in a single core context, being able to pause some work because you're waiting for something else is still valuable. And that's an example of concurrency. Whereas, like, you can't have computations take like literally back at the same time in that model. You can pause something and you can come back to it. And when you zoom that out to like a 10-second level, it might look like it's all happening, but it's actually showing. How are we going for time? We're half an hour. This is good. So apologies for the slip up on synchronization, but I hope that the talk of threads was enough to cover that. We'll look at virtual memory next, which is covered in the second half of some of this, I think. So to talk about blah, 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 blah. Is this going to take me to the right slide? Yeah. Yeah, so the main thing to talk about with virtual memory, there is an era of programming where there was or is no virtual memory. And actually, funnily enough, it still comes up all the time in current days, especially on microcontrollers. So in embedded programming context on small processors, typically there is no virtual memory because it's just like not worth having any extra silicon or stuff or power or whatever. So what that means is that like there's no virtual memory way of separating what areas of memory are used for what, or what memory space to feed from any running process. So processes all share the same memory space, and that gets really complicated. But it's the way everything used to be programmed. And it stems more from the thing with a microprocessor is that usually a microprocessor runs one thing. Like I'm trying to think of who can think of an example of a microprocessor use for me. Like I don't know, like a car control system. Can anyone just pull that out of that?
Like a sensor or something like that.
Yeah,
like door hand, like one of those automatic door.
yeah. So like you can so automatic door. It's like it might have a system structure that it's just like all it does is wait for open request. If open request comes through, service the door, open it. Then it's like a state machine or whatever, and it's like all it does is one thing. The difference there is like that microcontroller is not running different user-loaded programs, right? Like you never install an exe on your car microcontroller, so to speak.
It doesn't need to account for like an arbitrary number of efficient programs.
Yes. Typically in that kind of a context, you're compiling one program. There's not even an operating system per se. It's just one giant program that includes all of the stuff that an operating system might do, and you're just running that. So in that example, like that's where the single memory address thing kind of makes sense. It's just like, well, if it's all running one thing anyway, then there's not really a point in having all the process rotations. However, if you're building a more normal personal computer, with a user interface and you want it to be able to do multiple things at once or multitask, then that becomes really bad really quickly, because for multiple unknown programs to be able to share a single address space, like they have to be given separate chunks, or you have to use this old method called memory segmentation. I actually can't remember how it works specifically.
It's like just continuous blocks of memory.
I think so, yeah. It's like a very primitive version of virtual address. But that's where segfault comes from, funnily enough. Like, if you access outside the memory segment, it counts as a segmentation fault, which is where segfault comes from. And that was how programs broke if they read the wrong memory. And then virtual addressing was added, and they're like, well, the failure case is the same. We don't need to add another error code that other things need to be able to handle. We just reuse the same one. So it's still a seg fault, even if you access the wrong area of memory in a virtual memory based context. So yeah, that's the one that's one of the two main motivators for virtual memory, which is safe multiprocessing. Because if memory is totally virtualized, then each process can use memory like it's one playground for itself, and it doesn't have to worry about not stepping on anything else. And all of the virtual memory paging kind of like hides the reality from it, because it never sees any real physical memory address. But the second thing is also swapping, which is a topic that would have been covered, where all of a sudden, if you're running a lot of programs that are using a lot of memory, but not all of them are active at once, you don't necessarily need to keep all of the active memory in real memory at any one point in time. The best example of this is maybe a minimized browser tab. I don't know if you're like me, but I end up with 12 browser windows with 12 tabs each. My desktop on daily use in between the insane amount of systems you have to do a corporate job. But I end up with a lot of minimized windows. And so like you minimize the type, like it's not doing anything, but there's a whole bunch of state there, right? Like you've got certain pages open, the pages are in certain JavaScript state maybe or whatever, but none of it is running right now. So you don't need it to be in physical memory if there's something else you want to do, like, I don't know, play Minecraft or something. So that memory can be saved onto disk to pull it back later. And that's the general principle of swapping. In addition to that, nowadays, like memory compression is another swapping thing that happens. So say you've minimized the browser tab. If the tab's inactive, like you might still be able to save some space by taking all of the memory that it's touched and used and compressing it with a lossless compressor algorithm like gzip or whatever. And then all of a sudden, instead of it was using 400 meg memory, but we've saved all of that data to like say 20 meg. Like that's a really good compression ratio example. But this happens in Windows and Mac nowadays. They will compress program memory behind the scenes of stuff that you're not using to give you a little bit more room. And it's because it's just faster to decompress memory into other memory than it is to load it back off disk. So it's kind of like an extra second tier through all of this. But again, to tie back to virtual memory, I think like the reason it works well is because you have that unit. There's two things. You have the unit of the memory page, which is a very convenient thing to pull in or out of memory. It's a standard fixed size for the system. But not only that, when you have paging and when you have a virtual memory unit, you have the mechanism of the memory management unit to be able to catch. I think of how to explain this. Like when a program accesses memory, you get the page fault mechanism to be able to implement paging with at all, if it makes sense. Because virtual memory is in place, the way it works is that whenever a memory address is asked for, you go over to the MMU, well, the MMU does the lookup, and there's the TLB, translation look aside buffer, which is a pre-cached list of translations. And not only that, that's the pre-cache for the page tables. The page tables themselves are structures in memory that contain all the information about what page numbers are or aren't in memory. And there's the present bit associated with each one of those, right? And that's to indicate whether that virtual slice of memory is in memory or not. And then I think another one is like whether it's even allocated. Actually, no, it's whether it's in memory or not. What I'm getting at is that because that's baked into all of this stuff, whenever you access that memory address, the operating system can receive a page fault interrupt and then choose to do something with that. Because it gets the fault and the address the fault happened at, it can make a decision from that. And the decision would be like, okay, let's check the page table data structures or the memory allocation data structures. Is this a page that they should be able to be used or not? If not, okay, this was a bad memory access, seg fault, shut down the program. However, if it's memory that they accessed, but it's just paged out at the moment, then the operating system can take over and be like, okay, this program wants to access address 4997. And it should expect to be able to access it. It's just that right now the memory is paged out. And then you invoke paging algorithm, the page replacement algorithm, which is like, cool. Memory is full, probably. We've got to pick a page to knock out, put onto disk, so that we can put the other page back in to let that program run. And then once that's all done, the operating system does all of this itself in kernel. Once that's set up properly, it will then just drop back into the process to resume it at the same memory address or the same program address it was at just before. Then it does it again, accesses the memory, hey presto, it works, it gets the value, the program continues. So that's my best overview of why virtual memory is useful or done at all. Are there any questions about any of that?
I do have one question, but it's not strictly related to that. I was wondering if there's ever a situation that you would have a single process or program so complicated or in any situation where you would need memory management the way you would for multiple processes.
Like custom memory management almost.
Yeah, like if you have like a microprocessor and it's like, oh, that's only going to run one thing, it's fine. But then you actually put it on and it's like, no, this actually would, despite this, is there a situation where one process gets fuzzy enough for me, like,
You're saying it wants to have an influence on which pages are swapped in or swapped out or something like that? Because
there is a Linux system called madvise, which lets you say for a page of memory, you can give the operating system hints about how you're going to use it. And then so that can change the way that
the page replacement.
yeah, it can influence stuff that it's on Linux specifically. It can influence the way Linux might make decisions about it. It can still ignore it, but like there are scenarios where that can provide you better performance because you've told the Linux kernel, oh, I'm going to do a whole sequential read of this. So go and load everything in one go. And then at the end of the day, things are a lot faster. So I don't know if that answers your question, so to speak, but
I mean, you could, I guess, implement your own version of memory if you were like, you didn't have an operating system to rely on. Like sort of saying, it wouldn't necessarily be beneficial from the perspective of memory, like sanitization or keeping the processes separate, but it could be useful to gain that like virtual increase.
There is
like manually swapping stuff out.
There is another topic, and it's outside the subject, but there's a term called NUMA, and that's not the Numa Hey guy who's like one of the first viral YouTube videos. But NUMA means non-uniform memory access. And I got exposed to this in the parallel and multi-core master subject here at Melbourne Uni. Basically on really big systems with lots of CPUs and lots of memory, each CPU doesn't have the same direct access to the same areas of memory because of physically how things are laid out. So like one physical CPU core or chip will have direct access to some memory, but for other memory, it kind of has to go via a bus, I think, and that's slow. So it basically means that now all of a sudden it's non-uniform in the sense that some memory is really, really, really quick. Some memory is actually really slow because it's something else. So that can affect things.
You have to also coordinate like where all the memory is being placed, not just the.
Well, it becomes a scheduling problem, right? You don't want to schedule a program that's going to use a bunch of memory on the east side, we'll say, where you don't want to put that on a core that is west side that is going to have slow access to all those things.
But so that means you have to find.
Yeah, it's all probably a bajillion heuristics and guessing and stuff like that. So yeah, just going through these slides, what we've got, virtual memory helps. Yeah, this is something of like, if you implement some algorithm that requires scanning 4 terabytes of data, but you accumulate information along the way, and the accumulated thing is the result that you want at the end, then virtual memory allows you to do that linearly through memory without having to worry about the fact that you don't actually have 4 terabytes of memory installed in the system, right? Because you'll start accessing stuff, and then you run out of memory, and the OS will page away all the stuff that you weren't looking at. And yeah, that's another advantage of that. Well, I guess if you do that, you start accumulating a lot of memory.
It's probably going to freak stuff.
What's it? Yeah, but oh man, at work I see like I work at Commonwealth Bank as a site reliability engineer, and they have lots of corporate lockdown stuff on the laptop. There's this thing Airlock that only lets you run certain programs. That has a memory leak at the moment, and like it will get up to like 8 or 12 gig of memory, and you're just using your laptop. And you're like, why? So
In a restart.
yeah, exactly. I saw a screenshot of someone else on Microsoft To-Do's app was using 63 gig of memory because it had a memory leak somewhere, something like that. Anyway, so yeah, if we look at this again, I think this has covered what I was talking about in that. Yeah, well, we say allows programs to assume the program and data are in contiguous locations.
That's because you can spot the pages where we like.
Yes, true. That's another thing. But I was more just thinking like, yes, because the MMU hides that from. What I was more trying to get back at is that one key advantage of virtual memory is that for any program that starts, it doesn't have to make any assumptions over what areas of memory are used for what, like specifically what address numbers are used for what. It gets, say you're on a 32-bit computer, a 32-bit computer with 32-bit memory gives you about, it's 2 to the 32, which is 4 gigabytes of memory address space to work with. Any 32-bit program can essentially like use any number between 0 and 2 to the power of 32 for whatever purpose it wants inside its own program. And virtual memory will hide any actual overlap between other things automatically. Whereas if you didn't have virtual memory and you're on 32 bits of memory space, when your program starts, maybe you were assigned a slot from like 2 gig to 2.2 gig. And that's the memory you're allowed to work in. All of a sudden, when a program starts, like the whole program has to be relocatable, I think is the term that they use, where it's like the program has to be able to adapt to being plonked in a different corner of the memory space. That's what has to happen if you don't have virtual addressing. That's one of the reasons why it was invented, is that it just makes writing programs a lot easier because you don't have to make any assumptions about what memory numbers are in use or not, if that makes sense. And then there's that other benefit of swapping. That just means that you can make more efficient use of the RAM by getting rid of stuff that's not really being used, so that more active programs can run at the same time. More active programs can make more use of the limited memory in your system by vacating it for the active stuff when other stuff is not working. And one last term I'll mention again is there's a term called thrashing that's used in this context to describe what happens when you've got more active memory use than memory space. And I had to do this. It's basically like if you open Photoshop on a laptop with 8 gig of RAM and started editing really big stuff, you can run into this problem where, like, basically thrashing means that paging in and out is happening constantly. And because it's happening all the time, more time ends up spent purely doing the paging than time spent running the application. So the application just slows down a lot. And I ran into this with my 2011 MacBook Pro doing web development, where Chrome and Ruby, and then when we added JavaScript builds, using more than the 16 gig of memory I had on my computer, and like all tabbing between programs took like 5 seconds. So I had to RAM upgrade to solve that. It also had a spinning hard drive, which was really, really slow, so that helped as well. Okay. I think that's enough at this point. We've got here, last thing is the page table. What I would recommend is if for whatever reason you haven't gone through it, the one exercise they have in the workshops on page tables and memory address translation, definitely go over 1 or 2 of those kind of problems. Like
There's a few in the one.
in this one? Yeah. Exactly the kind of question you get asked in exams, being able to translate this, page size fit, things like that. And if you step through all of those things, I find those questions themselves explain all the moving parts quite well. There's a relatively simple formula that just understanding what numbers are associated with what part, like the virtual address, the bits of the virtual address, which bits go into the page table index, which bits are within the page, things like that. That question is will help you a lot there. At this point, are there any final questions about the operating system side of the subject? Okay, well, I hope that was useful. I'll hand to Colton now, I think, because we are.
We want to just make the introduction stuff and then we have a break and do the questions, or take a break then?
Let's go through the introduction and let's just talk through the overview.
Okay.
Then we can just like decide.
Let's see what we got. Cryptography. Yeah, all of these are animated. I don't even know how to do that on slides, actually. How do you make it to the dot points like individually animated? I couldn't do that. I could only make like the whole text box animated.
Yeah, it's really annoying.
There's a lot of stuff. Okay, here we go.
Just say
Go.
and I have been bent down with types that are not looking
I'm gonna sneak it up. Anyone say that, please?
But yeah, you have each difference or something that you might be just.
Yeah, no, not a problem.
My instant is confused. I think my first question. That's good. Like, I like this. Yeah, I like all that. Oh, hell we did something.
I'm not competing with pizza. I'm gonna let the pizza get. That's slice. Also, when you go back to I still
Yes.
I don't know. Like, sorry, online people. Pizza's arrived. We'll take a short break. What is Simon? What'd you get? Phone?
Right, there we go.
Yeah, that's important. Thank you. Feel good?
Alright, take care.
You want me exams? Yep. Yeah. We good to go? All right. Now we're full of pizza, ready for the second part. So I'm not going to spend too long on this. I've just done a brief summary of what I think is kind of the storytelling aspect for going through, the whole stack of the network. We have a bunch of slides at the end, which are more in depth, kind of similar more to what we breezed through at the beginning. We'll get the link to the slide at the end so you can have a look through that if you're trying to kind of drill or generate questions or whatever. But for now, just maybe 20 or 30 minutes. Hopefully we can get through this and then we can do the questions at the end in little groups and discuss it and then we got questions about. Okay, so the second part of the subject is networking. There's not too much overlap, honestly, between the first part and the second. It's kind of like almost two separate subjects. And this was Lachlan's bit. He is into the networking side of things. So yeah, that's basically right. The goal is we're going to really quickly run through the concepts, the core concepts for the networking, and there's a bunch of slides afterwards, which are here, but you could look through those in your own time. Okay, so realistically,
you know, a lot of people here are not going to necessarily go off and be network engineers. Yeah. So the purpose of what we're talking about at a high level is to kind of understand how this application protocols. Right. So ultimately, the goal is we want to be able to send HTTP requests, do DNS requests, do FTP requests, whatever in our applications. Okay. But to understand how they work and to debug things and, you know, have a general breadth of knowledge, we're going to look at all of the layers underneath that as well, so we can have an appreciation, understanding of how they work. All right, so we introduced layering here as a concept. We've seen layering before in lots of aspects of software engineering or other parts of daily life. But this is a really clean sort of discussion of layering because everything here depends on something underneath it. So ultimately, we're looking at the application layer. That's what we care about. But to sort of see how that gets powered, we go to the transport, internet, and network access layer as well. So, you know, we had some questions in maybe the very first Tutor section, like why do we bother with these layers? Generally, it's to do with abstraction. It's to do with the fact that, you know, these layers can do what they need to do really effectively, and we can have a good understanding of how they're supposed to behave. Testability in terms of, you know, responsibility of who's developing them, they can get a clean understanding of that, and then you can build on top of it. All right, rather than just have one giant implementation that does everything all at once, you can reuse things, whatever. Okay, so that's the benefit of having that layered-based architecture. And most of what we talk about in the subject is, like I said, about application level stuff. So I find that the TCP/IP model makes a lot more sense because 99% of what we're dealing with is IP-powered stuff. We're not thinking about alternative networks most of the time. And then we're thinking about, you know, on top of that, a couple of different transport layers. And realistically, we stop at our application layer. So we don't really think about session or presentation or whatever. So I'm just going to stick with that when we're going through these slides.
I think the OSI model was used in an era to talk about stuff well beyond the internet and like TV protocols and things.
Yeah, so there hadn't really been any kind of development of a sort of leading standard at that point. I think the OSI model was actually going to be something that was really implemented, and then it became more abstract over time as just a conceptual tool. Okay, so in terms of what we're thinking about, TCP/IP, I find makes more sense. Okay, so the bottom layer of this stack is the network access layer, and that is what enables the actual point-to-point communication across some physical medium between our physical devices, right? So if I want to send something between these different devices, step one is I'm going to be able to send ones and zeros between them. Right? So that is what the network access layer is dealing with. It manages those hardware devices and defines how data is being physically sent across some media. Oh, I don't know what I just clicked. Where do we go?
I think, why is this like taking? It's it was Safari. The Safari is what's running.
Hey, we're back. Okay. Yes, I can actually use that. Okay. All right, technical difficulties. Okay, so that's what we're doing with the network access layer. Most of the time, again, when we're thinking about this layer, we tend to think about Ethernet, Wi-Fi, maybe cellular. So Ethernet and Wi-Fi are kind of good things to consider as examples of this. Both of these, Internet and Wi-Fi, they tend to kind of just flood information around, and the recipients are able to kind of conceptually see the messages that are being sent all over the place, especially for Ethernet. It's quite true. But to be able to do this and to be able to address the different devices on this network, we have to have what's called what we call it a MAC, and that's a physical hardware address that's not supposed to change for a particular device. It's supposed to be effectively globally unique. And it's assigned when your device is created or when your network interface is built. And it's supposed to sort of stay like that indefinitely. And that's a way such that other devices that are on the same network are able to specify who they're trying to send information to, right? So computer over here is a computer over here. I want to send something to them, a bunch of ones and zeros. I need to know what their address is, and I'm going to kind of broadcast this time. Here's the message to that person, and they eventually see it, and they go, oh, it's a message from me. Great. So Ethernet, we've got down here, this is a very high-level diagram of the kind of structure for Ethernet packet. It's not called packet, what's it called? Frame. Yeah, so the data here is the Ethernet data. We've got a checksum on one side, and then over here is the key thing is destination and source map. So those are just saying who sent the message, where is it going to, okay? And this is within a very local scope, okay? So within Ethernet in your home, you could either literally have a bunch of computers like patched into the same Ethernet cable, or you can use what's called the hub. And this is kind of the traditional thinking around Ethernet, which is just someone's trying to send a message, and thank you, Stuart, for this diagram. A sends it, and effectively it just gets broadcast around the entire network. Right? Everyone is getting these messages, and what happens is C would just say, "Oh, this is a message for me, so I'm going to actually." Okay? There's a slightly more complex piece of hardware called the switch, which is actually able to learn over time the topology of the network and how these different components are, like where they exist. So that the switch can know, hey, if I want to send a message to device C, I've got to send it out on this particular port. Rather than just flooding it everywhere, it learns over time. Not super important, just like that.
No, other than yeah, the switch is more efficient, but requires a bit more logic. But yeah, it just goes to show that, like in the hub example, you can get delivered Ethernet frames that are not for your MAC address. It's just that you would choose to discard them if they're not for you, so to speak. So that's kind of the model of Ethernet, is that even though you need the MAC addresses because sometimes the message is broadcast to everyone, and you need to pick out what messages are actually for you, so to speak.
Yeah.
I just confirm, does having the link layer it's link and physical, because physical is the
little copper wire.
it's the actual wires, but the link layer is I think the physical layer is like binary signaling, whereas the link layer is talking about the Ethernet protocol.
Yeah. So this framing that we've got here, that's the link layer. The physical layer is going to do with what medium you're actually sending it across. So technically, you could use like a virtual Ethernet cable that uses light or whatever to actually transmit the data.
The best example is the difference between twisted pair Ethernet cables, which is normal LAN cable you see, and like fiber.
Yeah, exactly. Just use fiber. So the physical way, like again, in this context, what we're talking about in this subject, really doesn't make much of a difference, which is why in the model they're actually condensed just into the network access layer anyway. Because from our perspective, when we're thinking about networking, it doesn't really make too much of a difference. But yeah, it's a good question. Yeah. Point to point or end to end. So I assume that's meaning like
I remember seeing like the right. Like a bottle of this layer plus point. Oh, this would be for describing the difference between a direct cable connection to someone and being able to talk to someone over an indeterminate number of links. So, like, if you're saying someone the laptop, you talk to them like regularly, whereas any example will talk to the Google service. Taking Google to the city, you would much better city. Yeah. You have to use protocol that is end-to-end, not point to point, because you don't have a direct single wire connection. To like, let's switch to Google's servers. The really long spool, yeah, and walk all the way back on. Like, you don't have a way to directly sequence communicate with it. You have to rely on routing, which is audio stuff like installing the router somewhere. You can talk one end of it, and the other end of it you go to you can hold that goes to Australia and so like over multiple pops end up to but you don't have a point to point. You're not on a directly connected service.
Run the diagram.
Yeah.
Run the diagram.
Pretty sure that's point.
Yeah. But that would only be like the physical.
No, it would be so the way it comes up with this model is that the Ethernet is point to point thing because you can only communicate on. You can only do Ethernet communication to people on the direct wired Ethernet network. Whereas with TCP it might be because IP is recording and routing stuff that happen. that allows you to communicate across those intranets, across different networks because it's forwarded. And that's an example of intent. Because it's such a powerful thing. And it shows up in that diagram, it's like, I think it's like, even though from TCP going to AAP, you go like, oh, well, TCP to IP, AAP. But then for Ethernet, it's like, oh, it's your local network to the router to the IP building. IP building to say command or whatever. So that's the
oh yeah, grab the diagram, we'll have a look at that again. Sweet. Okay, so that was the network access layer, and the two that we tend to think about are Ethernet and Wi-Fi, at least in our discussions. Wi-Fi is actually quite similar to the switch, but it's going to be more complex. Like we'll have to think about things like encryption. And in general, Ethernet is not often encrypted. I think it can be encrypted, but it's just generally not. You tend to just trust people that are physically patched into your network. Wi-Fi in general is encrypted when you're setting packets up. Okay, so first question for y'all is, why did we not just stop with Ethernet? Why didn't we just have a giant worldwide Ethernet connection and everyone can just hop on and use their MAC address to send data between any two people? Why have we got all these other layers on top? Or at least, why do we have the internet layer on top of it? So what? How's that? Who's it more friendly to?
Well, we don't have to understand like the MAC address. We don't have to know the MAC address so everyone wants it.
That's a good point, but why can't we just have something in DNS like to deal with that? Because I mean, IP addresses are still not super user friendly either. Good point. Anything else? Let's go back maybe a slide. This is how we were saying this kind of works. We've got either a situation with this hub that's just effectively spamming everyone, or a switch. And the switch is kind of having to learn over time where all of these addresses are. So effectively, it's building up a bank that is supposed to kind of understand the MAC address for everyone on this network and who to send the packets out to onto which interface or which port so that they get delivered to the right destination. So what are the problems with either of those two if you're trying to connect the entire world together? Let's do the first one first. What's going to happen if you try and do this for the whole world?
That can come into play, but assume there's a standard here.
Yeah.
Why is the computer server not plugged into one hub?
Yeah.
And you can consider a hub. Well, first of all, I'm giving an answer of sorts, but you need a port for your computer.
Yeah, that's a valid perspective.
Consider that, like, in that model, you send one packet and it goes everywhere. Like, yeah,
you get a lot of that. You get a packet for every person ever sending a packet ever.
Yeah.
On the Australian internet. Yeah. The Australia-wide internet.
Anyone in ASU send it text messages.
Yep, you get it all. Unencrypted as well, yeah. Okay, so that's maybe why we wouldn't do hub, but what's the maybe counter argument for something that's supposed to be a little bit smarter, like the switch, where it's trying to make these a basic kind of routing decisions?
You need so much memory.
Yeah.
Yeah, that's pretty much it. So somehow this switch is supposed to be like a god tier switch that just knows every single device that exists in the whole country or the whole world, right? Not really feasible. And also, yeah, just getting all the traffic there would also use up. Like, how would you even, where does a switch exist? Like right in the middle of the outback and everyone has like an equidistant cable. Or like otherwise you'd have to run a bunch of cables individually to these ports. Yeah. Anyway, so the point is that it's fine for a situation where you've got a small number of devices and they're all hooked up. You can, blast out the message, spam everyone. It's not a big deal if there's only like 4 people. Same thing with Wi-Fi, right? Wi-Fi, you really can't stop it because it's just broadcasting in every direction. So you can imagine that's going to get crowded very quickly if you've got more than a few people connected to it. So yeah, that approach is just not really feasible, both the sort of flooding approach or the smart switches attack. So we got to keep going, right? We got to build up on top of that and add more layers to our model. Okay, so the internet, what it fundamentally is it adds the ability to route things without having a full understanding of where everybody exists in the whole world. Okay, so it's basically like that switch that we said before, except there's some sort of structure or grouping to your IP addresses, such that the routers can know roughly where to send things to get them closer, without necessarily knowing exactly, like having some mapping for every IP address that exists. Okay, so in general, as a concept, the addresses are supposed to be sort of prefixed in a way that geographically they're near each other. That's kind of the general concept. Okay, groups of IP addresses wind up being close together when you get small enough, and that means that you can have a routing table of a reasonable size, such that you can make routing decisions to say, hey, like I'm in Germany, I've got a packet for this person, this IP address. I don't necessarily know that particular IP address. I've never met them in person. Maybe I've never delivered a packet for them ever, is this router, is what it's thinking. But I've been told, if Zoom will get out of the way for us to be able to actually see, maybe we can't see that.
You can.
Oh, there we go. Ooh, okay, just delay the problem until there's something at the bottom of the slide. That the router is somehow aware that this direction has something to do with this, like some prefix here. I can't remember. I thought I had like an animation for this. Oh no, Zoom's taking over. Okay, yeah. So the router has a thought, which is that it doesn't really know exactly who this 203.132.68.108 is. It's never met him before, but it's got some note in its routing table that says IPs that start with, maybe in this case 203.132. They should be routed to interface 1 because they're geographically closer to wherever that router is going. Right, so we've got some sort of hierarchy or some sort of structure to our addresses now, rather than MAC addresses before that were just unique to your device. So you can identify the device, but there's no logicalness of that. Okay, so part of the difference that winds up happening as a result of that is that your IP address of your device will change over time. If you move countries, your IP address is going to go with it, right? Or it will change. Sorry, it won't go with it. It will change, but your MAC address will stay the same no matter what country you're in or where you visit or what network you're connected to. It's supposed to conceptually stay the same. Make sense? So the IP address is more about your location and getting data towards you. All right, so that's kind of the important thing that we've added here in the internet layer. Okay, so properties of the internet as a network. It's best effort, right? So that means that you send a packet, that's great, but it doesn't necessarily mean it's going to be received. Right? And that's really important because that will factor into what we think about later with our transport layers. Okay, so at some point, if a router has too much stuff going on, all its buffers are full, it's stressing out, it might just drop your packet and say, I'm really sorry, I couldn't handle this right now. All right, the other thing is that order is not guaranteed. It could be the case that you send things in one particular order and then get delivered in, right? So it's not trying to promise anything to do with ordering of what you've sent. So you've got to deal with that yourself. Right, so it's a datagram network as well, as we just talked about in, I think, week 11, maybe it's week 10. But it's not a virtual circuit network, so you don't have to do a routing per connection. There's no real connections at all. It's dealing with particular packets that are fully addressed to where they're supposed to be sent.
We just see it.
Compared to it. And then virtual circuit. Okay, so yeah, and we also just like, again, that routing protocols, that was like a whole lecture. And I'm not going to throw that in here. There's more slides on it later. But just to remind you that the protocol that gets followed for actually delivering an IP packet, with an IP address to its destination is separate from whatever you have to do internally within your network to map the topology and then do like we did with Dijkstra's to figure out what the shortest path is, whatever between these places. That's like a separate sort of process that you'll have to do as the owner of that net. And the routers do that using their own algorithms, however they configured like open short path first. And we kind of play around with that at a very basic level with just Dijkstra's and thinking about the weights of path and how you can manipulate the edges. Okay, so again, key things, best effort, order not guaranteed. So same question as before, why don't we just stop with the internet layer? Why do we have additional layer on top of this? What is the transport layer going to add?
Reliability.
Yep, great. So maybe we want reliability and IP doesn't promise that. Security, what about security? Yeah, I would say that kind of falls, it depends on what you're thinking about in terms of the TCP/IP definition. I would say that would fall more to the application definition, technically, like TLS or something. But then we have been talking about things like QUIC, which are inherently TLS protected, and we call that a transport layer. So it's kind of ambiguous.
I think I have another way to think about this. If you've just got IP address communication, like, what does that grant you the ability to do? Mention reliability is just a good point, and sort of one of the two main things. Obviously, like with IP, you can deliver a chunk of data to a particular IP address. Or you can make a better data set together there. But if you've got one computer and another computer, all you can do is send arbitrary payload of data between the IP addresses. Excluding reliability, what else can't you do? What are you limited by? You've got one computer to check, but like how much stuff are you running on your computer?
You can kind of go through the list of TCP features, to be honest, and each of them like
yeah,
a short
but it's more like when you move IPC, TCP, or UDP, ports to introduce. The point of a port is the automatic multiplexing between different things on the line.
Yeah.
So even though you can reach an IP address, like someone might have a server on the internet that handles email and runs a web server. How do you know which of the two things to call on the server? If you just have IP, you need an additional way of being able to work out how to talk about the right thing. Yeah. And then not just that, also like connection session as well, multiple connections to that thing. How do you differentiate between each? Like you've got 5 connections to a server, how do you split the 5 connections up before you have the percentage of data to the other end?
So both of the transport layer protocols that we've discussed in this class, we did TCP, what was the other one? UDP, right. They had one thing in common, which was what? Yeah, the ports, right? The port number was the main. UDP adds very little on top of IP, aside from the port number. It has like a really simple checksum, but that's not actually even useful in practice because it's too simple. So the main thing that UDP adds, it's effectively IP with a port number. And the port number, what that allows you to do is not just have connections between one device or one network interface and another device, but to have connections between some other definition inside of whatever it means to have a connection, right? So you could have like one application conceptually connected to another application. An application can open multiple ports, like you've experienced, right? Maybe you have a port for one purpose to issue connections to do with like joining something or whatever, or then a different port open for a different reason, different kinds of connections. Maybe to the same machine, so you could have multiple connections open at the same time. Browsers do that all the time. That's how one browser can have multiple TCP connections to the same web server by opening multiple ports.
Does anyone here have two web server assignments? Two subjects at the same time? One laptop at the same time? Never mind.
You put the port number.
Actually, I run I use Blast, the Python demo. The default is called 5000. And I have like 8 unique Blast things over. If you run one, you got to run another one, and you're like, oh, port 5000 is already 52 there. And then I go, oh, default that's one. And then I do that.
It can't detect that may fall over for you.
Sometimes they do, but so I end up in a situation where I have a different pattern for ports. I can't remember that.
Yeah. Yeah. So the concept of a well-known port is okay. So good. We had some good answers, and effectively the list here is really kind of just TCP stuff. So TCP is kind of like UDP's benefit of the ports plus extra stuff, right? So we are graduating from host to host to port or socket to socket, whatever you call that. And we maybe want to fix some of these other things that IP has inherent in it, which is that there's connectionless, it's best effort only, there's no auto guarantee, etc. Okay, so we're going to build on top of that with our transport layer protocols, and depending on which of those flaws, potentially, depending on how you view it, we want to fix, you choose your transport protocol. Okay, so UDP had the port number. So just to summarize, anyone want to try and regurgitate what we were just talking about? What does the port number do for us? Yeah, it's like you can have, if your laptop or whatever is receiving a bunch of packets from somewhere else, you have a little label on them that just says, you know, which pigeonhole. Basically, you've got a mailbox in your laptop that has 65,000 slots in it, effectively. Okay? And when something gets delivered, because of the UDP port number or TCP port number, it can be put in the right slot. And then the application that owns that port is able to, or the socket that's associated with that port, can then go with, there's more to it than that. Like there's actually, you can have more stuff. And that's how many port numbers are. You can go in and you can specifically just grab packets that arrived for that, right? So that means that your application can be receiving things separately from a different application. And that's one of those core abstractions that we talked about at the beginning of the subject, operating system abstractions with sockets, which we'll talk about instead.
And like if you didn't have ports, instead of pigeonholes, in the main example, there's just one big hole in the wall.
Yeah, you have to like sort through it or have some other mechanism internally within the data to be able to recognize that this was destined for this particular listener. Great, so that's just putting that in. Okay, so TCP, it has the same concept of the port number, so everything we just talked about. But its goal is to make a network connection behave like a string. Ultimately, that's what its purpose is at a high level, okay? It's trying to make sure that everything arrives and it arrives in a form. So you can read from the network like you're reading from a file. Okay? So that's really nice and convenient to do as a programmer because you're using the same interfaces as what you use to get a file from my hard drive as I'm now going to use to download something from the internet or access something from the internet. I can read it like a stream. Okay, TCP also has some other quote unquote nicenesses to it. We had flow control and congestion control, and we talked about those two things. So this is TCP kind of being a good citizen in a way. It's being aware of its environment and its surroundings. IP is very much just you can send as much as you want conceptually, and it's just going. Flow control is about not overloading the other side of the connection. So whoever you're connected to, they've got maybe some restraints in terms of how many packets they can hold in their memory buffer before they get overloaded. So that's to stop you from spamming them too much. And congestion control is supposed to be an attempt at stopping the network from being. Okay, so it's detecting by a loss of packets, like a lack of acknowledgements, that things are getting dropped by the network. And it takes that as a proxy for meaning that the network is overloaded. So it will start backing off and send fewer packets per time. Right? And we've seen some of the algorithms for how that works. There's a few different variants over time. These changed in terms of exactly how it works, but it's roughly the same sort of thing where it's kind of growing over time. Every time it's receiving these apps, it's increasing the speed that it's sending things at, the frequency that it's sending packets. And then when it starts missing acknowledgements, then it drops back down and grows up slowly again. So it'll go through these cycles. Okay, so that's just, again, TCP, aside from being an approach at making the network look like a stream, it also is doing some other nice things just to keep everybody sane. Okay, so just comparing those three, IP was host to host, so you're able to send messages from one IP address to another, so one network interface to another. UDP and TCP are port to port, so you can read that as approximately to do with sockets to sockets. Really is more accurate than port to port. Okay, because ports don't really exist; they're actually just identifiers. That's why my analogy before with the number of pigeonholes you have is actually wrong. But the key thing is it's just specific sockets. Okay, so delivery type, UDP and IP are both best effort because UDP is basically just IP with port number. And then TCP, through all of its efforts, with all of those acknowledgements and all of the back and forth checks, it's able to maintain reliability and it delivers things only up when it's in order. Connection state, IP and UDP are both connectionless because again, UDP is just IP. TCP is connection oriented, and that's almost by necessity. It kind of has to be connection oriented so that it can maintain the state about what's been sent, what has not been received, etc., so it can retransmit. That necessitates keeping state about a connection that exists. And then the other features that we just mentioned, IP, that's the baseline, so there's nothing on top of that. UDP adds a very basic checksum, which in practice is not very useful. And then TCP has the flow control and congestion control that we've spoken about. And that has to do with it just being a good team player in the network. Okay, so then we also introduced the concept of a socket. And this is what I was talking about before, that this is just a, I don't know how to move this.
You got to click on the black bit of it.
Yeah.
Drag.
Okay.
It weird.
I felt like I was going to click on the button. Okay, so a socket is just an interface for us to be able to interact with these transport layers effectively. That's what UDP does. The TCP, UDP, they're so well known that basically any operating system is going to have an implementation of that in the kernel itself. Any reasons or any suggestions, why is it best that those live in the kernel and not in user space? Why is it great that TCP in particular maybe is hosted in the kernel? Like you don't have to run some program or import some library and run it. It would be very complicated if you had to write it yourself, absolutely. But let's say that you could just import a library instead. Yeah.
So because if you had to do it yourself, you have to manage memory, like management stuff. What else would you have to manage? You're running a program on a computer. You want to talk to the network. How do you do that on the computer? Like say you've got a network card, you've got to talk to the network card. So yeah, so drivers are the drivers are using kernel.
Is that something that you think any normal user land program is able to just do by itself, interact with the network card? No. So how's it going to do it? Yeah. So what was the term we used for that? System call. Yeah. All right. So you're going to have to do a bunch of system calls constantly if you're running this in user space. So it's really nice that your operating system has these implemented inside of the kernel. Okay. So what that means though is that you need an interface to be able to play with them, right? You need an interface to be able to create a new TCP connection and monitor its state potentially or whatever. Okay. And so the interface that basically everyone has standardized on is called the Berkeley Sockets API. Okay? We just call it the socket, and we talk about it like it's some sort of like God-given implementation of how you must create a TCP connection. But that's actually not the case. There are plenty of operating systems which do things differently. Plan 9 is a really interesting example. But all that I want you to take away from this is that this is a socket interface is just a nice way to play around with these transport layers, and it's become very standardized. Basically, everyone uses it. Even people that or operating systems that don't really use it, like Windows, they kind of copied it, and so it's the same thought process to be able to use it, even though it's not literally like binary compatible or Unix compatible.
They tried their own thing with WinSoft, and then I think just Berkeley sockets was better, and they ended up copy pasting.
Yeah, I don't know the story, but it's basically the same thing except with some extra flags that you can set for like Windows specific use cases.
As a small point I want to make, we were talking before about that example of how why is this in the kernel? It's because you shouldn't be able to just expect a user space program to talk to the network card arbitrarily. That comes back to week 1 of the subject on what's the point of an operating system. And what's there's 2 points of an operating system.
One is the abstraction.
But the other general management of resources. Yeah. It's that fact of like, well, yeah, you want to make sure that there's careful interleaved access to that, so that you can't read network data from other programs. And step on other things, stuff like that.
But you could still do that through a system call interface. It would just be more cumbersome, I guess.
It'd be a lot more. Well,
it'd be equivalent to like file.
Well, yes, but like the immediate thing becomes concurrency relatives. Like if you call write on it, whatever.
Oh, you're saying multiple programs sharing the same socket?
Same network card.
Okay, yeah.
They didn't have a socket API, all they had was the ability to directly talk to the network card. Okay. Then yeah, you'd be able to then you'd be able to break out the model of ports and you'd be able to
I was still assuming it would be buffered by the curve before getting the card, like as in there would still be something.
There is as well, yeah, but again, I just wanted to mention because it ties back that thread of like.
Yeah, and we've got the other classic picture here that we love, which is the ugly interface and the beautiful interface, and sockets are one of those.
The other example is that you'd need to know how to speak to every possible type of network card in every possible computer.
Yeah, if you had direct that.
If you didn't have a standardized API, so you have a standardized API.
Yeah, so now we're back to where we started, right? We did all this work to get where we were originally talking about at the beginning when we switched into the network side. So we've done all the work, and now we can actually have some sort of application protocol, which is pretty funny because I think a lot of people would still think that HTTP is not low level, but it's about the lowest that a lot of people will get in terms of when they're thinking about being a web developer, etc. You usually don't have to do too much in terms of if you're writing JavaScript, you never think about TCP. You just fetch something and you put an HTTP address, and it comes back and it's magic. All right, so we talked about in this subject HTTP, SMTP, and DNS. I don't think we covered anything else, did we? Those were the main ones. Yeah, they're the ones we spent a reasonable amount of time talking about. So HTTP was the first, or one of the ones we talked about anyway. It's powering the web effectively. It uses TCP, so it relies on TCP because it expects everything to be delivered in order and reliably. Right? So that's a thing that it can just work with and not have to manage its own order or whatever. Right? It's nice to be able to rely on those guarantees. HTTP is call and response, except in one edge case, which is you have server push enabled on the server. And I think that was mentioned in the tutorials, but it's really not an important edge case anymore because it actually doesn't exist in browsers anymore. It's been totally eliminated because it was garbage. It destroyed cache.
Is this the thing where it can send you a file at a time?
Yes.
Yeah.
So the idea was supposed to be you ask for a web page, and the server knows, hey, web page has like 5 images on it. So you're going to be back in a second asking for this. Let me just save you the effort and send you 5. But as soon as you refresh the page, it breaks everything because you either have to be, or it doesn't break everything, but it just means that they're going to send you those 5 images again rather than your browser caching them and being able to reuse those assets, right? So it kind of invalidated the browser side cache. So that's not super important. The main thing is that it's call and response. You make a request, and then you get a response of some kind, and then the interaction is done. If you want to do more stuff, you make another request, and then you get a response. Okay. Okay. So HTTP 1.1 was, so prior to HTTP 1.1, the call and response required a new TCP connection. So if you want to go get something, you open a TCP connection, you issue the request, you get a response, and then the TCP connection has to die. That was convenient in an era where you weren't really getting a whole bunch of linked resources. It made it easy to figure when the body of the response was done. Because when the TCP connection closed, when you couldn't read from it anymore, then you know you got all of the data that was at the end of that file, whatever it was, your HTML file, your whatever. Okay, so it makes it really simple. HTTP 1.1 added persistent connections, and that's kind of one of the biggest leaps, which meant that you can actually do multiple request response chains on one TCP connection without closing it. So, question for you, do we remember, how do you then signal A, the end of the headers and the start of the body, and B, the end of the body? Because we now need to be able to differentiate between, the second case is new, right? This was still important in HTTP 1.0, but let's just take our understanding. A and B, how do we do that?
And then it's just like 3D lines.
Yep. Perfect. What about the second one?
Well, so if you send all your headers,
Yep.
send you 2 new lines, and then you send all the data, how do you know you're getting the data? Like from the other side, like pulling bytes out of the stream, how do you know when to stop?
Not done it.
Sorry.
Not done it.
Good thought, but not quite.
What if it's an image that has random bytes?
Yeah. Or the image itself has a null. You're sending something across that has a null.
So you might need to actually bring it up. How do you have to stop?
Yeah. Good thought. That's how we did it for the headers, not for the body.
The data could have.
Yeah. Maybe just send me an example of an HTTP request. Oh, is there? Well, let's see on the picture. Which header is going to help? Content length, right? So see that one there? It says 30. So that means that there are 30 bytes worth of information. And once you've read those 30 bytes, then okay. And then anything else coming in is going to be a new request.
In general, variable length data transmission, there are two options. One is length coding, so say how long it's going to be. And then the other is being able to signal the end, particularly using a magic number, so to speak. But you need a way to be able to escape that number that you can perfect depending on itself.
Yeah. HTTP still runs in that problem as well. Not worth discussing, but there are multi-part uploads as well. So you've got multiple parts in the body, and then you need to generate a unique instance variable. So we don't care about that. We're just going to remember there's a content length, and that's how long the body is. And when you've read that, then you're finished. And that's nice and easy. Okay, so CRLF and then content length header for the second part. Sweet. All right, so we've done 2 of the 3 that we were interested in from the beginning. The last one is SMTP. So simple mail transfer protocol is, I guess it's simple in a way, like it's supposed to be very vocal, but it's not particularly simple from the number of exchanges we need to do to get some very simple work done. But this protocol is very old. The way that it works, for instance, is conceptually, like if I've got some mail on my laptop that I want to send ultimately to my friend's account, if they're on a different mail service, I would use SMTP, or my device uses SMTP to send the email from my device to my provider's mail transfer agent. And then generally, then that mail transfer agent will transfer it to the final destination, possibly via intermediaries as well. Okay, so Gmail and Outlook, for instance, might have a long-running session with SMTP, and it might exchange a whole bunch of messages before it closes, if it ever closes. I genuinely have no idea. I assume they're just always sending messages. But the shortest kind of conversation you can have to exchange mail involves a hello, conversing about who it's from and the recipient, sending the mail. You have to use a dot to indicate that the message is done, which I think we talked about in tutorials, which is a very interesting point. It's not that hard to have a line dot on it. So you got to do some extra work to make sure that that doesn't get in the way. And then you can quit at the end, right? So if you had more than one message to send, you could repeat steps 3 through 9 and send more than one message. And yeah, it's not for other notes. It's not for retrieving mail from any kind of mailbox. So when you actually view your mail, you have to use a different protocol, either IMAP or COMP3, those are common ones. It relies on TCP, so again, it's just nice to have those guarantees built in for us, so you don't have to worry about, you lost the packet at some point. And because this is a really old protocol and it's the way that we use the internet has changed a lot, it's got a lot of round trips built into it, and it's ASCII only as well. So it makes it really hard if anyone's ever tried to encode things from email, it is non-trivial to put HTML in email, and you have to do some more weird stuff. So you can't easily embed things in, you can only put ASCII characters in.
Most importantly, though,
yeah,
has to be from the roots.
Yeah, you gotta escape everything. yeah. Anyway, yeah, people have solved that problem for us, but it's not nice that we kind of have to rely on that.
HTML email is one of the worst things in technology.
Yeah. You've spoken like someone who's had to do this. Okay. So the last one, sorry, that wasn't the last one. The last one we're up to is DNS, and this is kind of it's an application in a way, but it's sort of something that we need as part of some other use case, which is going to be accessing the web via HTTP or whatever we're trying to actually interface with. So the way that this works, we've talked about this, but basically its purpose is to resolve some human readable host name, which is like google.com, over to a set of either IP addresses or for the web server, or an IP address, or actually no, it's not an IP address for the mail server. It's going to be a canonical address for the mail server, or potentially any other kind of custom records you want to put in as well. So it's really just a distributed database that you can use to look up IP addresses from host names. Effectively all we need to think about. Okay, so this one, differently from the previous two, actually doesn't use TCP, it uses UDP. So my questions for you are, why are we not using TCP? And what extra work does that mean we have to do if we've got some process or application which is supposed to be doing this DNS querying for us? What extra work is there because of this choice? Yeah.
Like if you made it all right, but it's not very, it's pretty bad. The microphone stuff not very powerful. But with you just trying to get this giving the address, so you just keep spamming no matter what.
Yeah.
Just gonna try.
So what are the word I don't know?
I don't know. It's just it doesn't matter. Like how you said, it's like it doesn't matter if it's spam.
Yeah. So there's no additional effects if it happens more than one. It happening one time is the same as it happening multiple times. Here, it's kind of obvious it's idempotent because we're only reading from a database. We're not actually changing any state at all, right? So we can issue as many read requests as we like. It's not going to affect anything. So it's kind of trivial that this is idempotent. But there was one other thing. So if we lose the packet, we just got to set a timer, and then after the timer goes off, like, oh, it's gone. All right, we'll just try again, right? But what about the other thing that TCP gave us, which is that it works as a string? So do we need that here, or how do we get around that? But how do we ensure that, like, it's kind of giving it away by asking it this way. So if you have a big, some sort of big amount of information you're trying to send over TCP, it will break that up for you, right? And sometimes the IP layer might fragment it even more, but it gets put back together at the other end. So why don't we have to worry about that fragmentation or out of order delivery for DNS? Yeah.
No connection.
It's connectionless, yeah. So the key word that I was looking for here is that we just make sure the amount of data is small enough to fit into one resource size. Yeah. So that you don't have to worry about fragmentation because it's sort of an atomic request response. They'll fit into a reasonably sized. Cool. All right. And I think we talked about this sort of fan approach in terms of the authoritative server or whatever. But you have whatever your local DNS server is. Sometimes that's your router at home. Otherwise, if you're in a bigger organization, you might have a more dedicated machine for that. And that caching result as well. So if you ask for the same lookup multiple times, it will probably have a cache there for a while. But otherwise, if it doesn't know, it'll go off to the root server for, like, if you're looking for beta.example.com, it'll go for the .com. So it'll go for the root server, and then it'll come back, and then it will go over here to the top level server for .com, come back over here to example.com, and back, and then maybe finally to beta.example.com. This is pretty extreme that those two would be different servers, to be honest. Most of the time, once you get down to a particular domain, it would be the one or a server, but it's just an example because you can. So one more question, actually, just to throw it out there. Why are we making the local DNS server do all this work? It's like, why don't we instead design the protocol such that the root server is the one that contacts the top level domain server, and then that one contacts the authoritative domain server, does the chain for it before coming back? Why?
Because you're each has kind of for yourself with the DNS server, with the machine itself, it doesn't know where to go to actually. So having like let's say one.
Yeah. Okay, that's a good point. So that's how you get your initial DNS server connection, right? So that's talking about this here, right? Like, as in your device knowing where the local DNS server is, and that actually gets served up when you connect to your network by DHCP automatically. It'll tell you. You can manually override it if you do like what you said, where you say, I want Cloudflare, or I want Google's DNS. But I was more asking, why is this like a fan type structure? Why is this one going off here and going off here and going off here and going off here, rather than it just going to here and then this one querying here, and this one querying here, and this one querying here? Yeah. Yeah. Absolutely, right? So if you do that, they need to become stateful. And these guys are important. They're busy. We're not important, right? they're dealing with lots of requests, and we're just over here, trying to download Minecraft or whatever. So it's really not important.
Websites.
Yeah, exactly. There's a few, I think. So that server is definitely, if it's still a beige box like that, it's maxed out. Okay, so yeah, like we said, it's faster. So UDP, you don't have to set up a connection or anything. Did you have a question? Sorry.
Yeah.
Yep.
So when you type in like Google.com,
Yeah.
it's not your machine links page. It still asks on DNS servers and DNS servers page.
That's a great question. Your machine actually has its own internal page.
Oh,
Yeah.
okay.
So it goes through tiers of caches. But if you hadn't queried that before, then it will go. Great. Okay, so yeah, it's faster using UDP versus TCP. There's no handshake. Remember, TCP, there's a lot of back and forth just to set up the connection, and less stress on both machines because you don't need to start, setting up memory and other data structures to be able to handle that. And it's less stress on the DNS servers. Okay, so like I said before, there are now a plethora of slides for you to go through and in your own time. Some of them I have cannibalized and reused certain diagrams. But a lot of these slides are good to read through, but we don't really get enough time to kind of go through all the moving parts of the entire network stack in 2 hours, or 1 hour even. Yeah, if we could get through the whole subject content in 2 hours, you'd probably be worried about the value for money you're getting from the subject. So there's a lot here. And if I get to the end, maybe there's a faster way to do this. I'm sure there's a better way to do that. If we go to the, oh no, the mouse is backwards. Okay, so we're here.
It's my arm. Is my arm.
I think this was new. If you want to do this, you can do the exam study steps. Like we said, it has a lot of stuff.
General notes I give about the subject, obviously it's a big subject. I'm pretty sure it's been feedback point year after year after year after year to the few subjects, but it's complicated, I think. The two advices I give are what I found really useful is breaking the whole subject down week by week. And don't mind sort of what product week by week by and whatever. And once you group that, look at this and go, what's going on, but if you go back to how it goes. The second piece of advice I believe, especially if we operate with more relevant earlier, there's so much that interrelates with the operation. CPU access to memory, but it accesses virtual memory. The virtual memory goes with you, and then the virtual memory space. It's a process layer, it's a huge web.
Yeah, I think that can be summarized. Everything here has a place in computer science. It's all been designed by people for a reason. Like there's nothing in there that's decidual for the most part.
Yeah.
It's not like you're doing a natural science where we're going to go study the planet and different core. Like we have to learn stuff. It's all there for a reason. You can go through a history that, okay, I know exactly why this is like, because this guy at this point did it.
But also it's like because don't freak out, you don't understand all the points. Like every time you go through a different example that touches different interconnecting parts, it'll make more sense the more you've done it because you see more of a part of the things like that. You come back to paging, you remember a bit from virtual memory or whatever, bit CPUs and caching or whatever. So every second time you go through the web of concepts, you're better prepared to understand it.
Yeah, I think that's definitely a good point. Like even if you don't get it, just keep going and then do a full circle, come back. Like finish it and then come back and do another pass. That's a good point as well. Drink water. Drink water. Okay, thanks for coming. So I don't know what we're doing time. We're at 10 anyway. So much for only being 20 minutes. Sorry. But there are the slides here. I assume we're able to give these out. And there were questions that we were going to do if we had time, but I guess we didn't. We can ask on it. Yeah. Oh, there's this as well. I don't know if you guys. Oh, I'll leave this up to get a quick photo of that if you haven't got it. I don't know if this is still active. This survey slide, or is that?
Let me bring it up.
I feel like that's probably just been there since
It's a Google form that it's asking me for access to.
Okay, then you could say. Well, it might be because you're not in. You're not in. Oh, sorry, yeah.
You feel off, we can just get a photo this on us to be really nice.
Gotta justify Domino's, man.
Yeah. So we're supposed to come in the front of the roof with you. We'll take 30 seconds of the class, we'll do it for everybody.
Bye. Thanks a lot.